General relativity tells us that space-time is curved. What does that mean? Well, there are two very different ways of looking at it. But before we look at curved space-time, let's look at curved space without time. Here is a spherical surface, like the surface of a planet. A sphere is a two-dimensional surface that curves around in a three-dimensional volume. We say that the surface is embedded in a higher dimensional space, 2 dimensions inside 3 dimensions. Next, we want to draw a straight line on the sphere. But what do we mean by a straight line on a curved surface? First, let's look at a plane. We have this cart, and later we'll think of it as a particle. There are 2 wheels connected by an axle. The 2 wheels are the same size and they rotate at the same speed. And then, of course, the cart moves in a straight line. It drops little coins that leave a trail so we can see the path. Now, if one wheel rotates faster than the other wheel, the cart will turn. And if one wheel is bigger than the other, the cart will also turn. And you could imagine that depending on where the wheels are on the plane, the sizes change. But for now, let's not do any of that. Let's just go straight. Now let's put the cart on the sphere and let it loose. It'll do its best to follow a straight line. That line is called a geodesic. On a sphere, the geodesics exactly cut the sphere in half, just like the equator on Earth or any meridian. Before we move on to the second way of thinking about curvature, let's look at how you can know whether you're on a curved surface or on a flat plane. For one thing, you can try to make a square. To make a square, take 4 sticks of the same length. Put one stick horizontally, then another at 90 degrees. Now start at the initial point and put one stick vertically, then another at 90 degrees. And there, you have a square. But what happens when we try to do this on a sphere? Put one stick along the equator, then another pointing north. Now start from the initial point and put one stick pointing north, then another going west. It doesn't work. The endpoints don't line up, and the final angle is larger than 90 degrees. Another thing that differs between a flat and curved surface is what happens to parallel lines. On a flat surface, they stay parallel forever. But not on a sphere. Here are 2 carts at the equator. In the beginning, they are parallel, pointing north. But as they move north, they get closer, and at the North Pole, they collide. So that was the first way of looking at a curved surface, that it's embedded in a volume. Just to avoid a point of confusion, our 2-dimensional surface is not the same as the 3-dimensional sphere, like the planet Earth. The surface is the skin of the sphere. If you or I stand on a planet, we stick out in the 3rd dimension. We look up at the sky and down at the ground. This is very different from being a 2-dimensional person inside the surface itself. We should really think of this guy as living in the surface, as if he were made out of the pixels that make up the surface. The same goes for the sticks and for the cart. They are all in the surface, made of pixels. In the second viewpoint, we get rid of the 3rd dimension. Let's take a sphere and make it flat, as if we wanted to make a map of the world. For example, we could simply press down on the northern hemisphere, then rip a hole at the South Pole and pull up the southern hemisphere. There are many ways to make a flat map from a sphere, but you always end up with some distortion. If you look at the pixels that make up the sphere, they're all about the same size and shape. Here we highlight some of the pixels with red. We will start to think of the pixels as the building blocks of space or space-time. Look at the red pixels on the flat map. Some are very distorted, stretched long and thin. The building blocks of space are no longer uniform. We can now look at what happens to the geodesics, the straight lines that the cars created in the shape of circles. They pass through pixels that's been distorted, and therefore they are distorted. We can add some sticks on the sphere. Think of the sticks as pieces of geodesics, straight pieces of lines. On the sphere, they're all the same length. If we think of the sticks as also being made of pixels, it makes sense that they too should stretch and bend. And they do. On the flat map, these sticks change in size depending on where they're located, but also depending on the direction they're lying in. Remember that on a sphere, we cannot make a square from straight sticks. On the map, we cannot make a square of crooked sticks that think they are straight. Remember that even though the map is flat, it represents a curved space. If you were that flat guy inside the surface, you would think that the sticks are straight because you are made from the same distorted pixels as the stick. And just to complete the picture, here are the lines that are parallel at the equator, but only at the equator. On the map, they never look parallel because of the distortions. There is an old riddle. If everything doubles in size, including you, would you notice? Well, no, you wouldn't. You double in size, the measuring stick doubles in size, and the things you measure double in size. What we have is something similar. If you deform and your stick deforms and the things you measure deform, you won't notice. And if things change in size as you move from one region of space to another, you wouldn't notice anything locally. You might notice if you compare things far apart, for example, by making a large square, as we saw before. But locally, where you are, you will not notice. With that in mind, let's return to our cart. Remember that on the sphere, which is not distorted, the wheels are the same size and the cart moves along a great circle, which we highlight in red. But when we make a flat map, pixels and sticks change in size, and so do the wheels on the cart. We saw before that when the wheels are of different size, the cart goes in a circle, and that's exactly what happens. The cart thinks that it's going straight, and it does follow a geodesic. This is why we can think of the cart as a particle. It is not an infinitely small point. It has a little bit of width, so you can sniff out the environment and notice if things change, if there's a gradient. So we have seen two ways of thinking about curved space. We can have a two-dimensional sphere embedded in a three-dimensional volume. Or we can get rid of the third dimension and deform the pixels, which are the substratum of space. Is one better than the other? Well, both are accepted viewpoints. Richard Feynman has a lecture on what he calls a hot plate, where the size of objects depend on temperature. His hot plate is a flat map that we have seen. I recommend checking out his lecture. Kip Thorne likes to use both. He writes, physicists can and do use the two viewpoints interchangeably. Which viewpoint tells the real truth is relevant for experiments. In this video, I prefer the second viewpoint, where the pixels of the substratum bend and stretch. I find it much easier to visualize and get a gut feeling for what's going on, as we'll see later on. It also fits nicely with quantum mechanics. I'll see you in the next video.